So the last class we were talking about RCBD, which is your randomized complete block design, right. So we talked about what is the hypothesis, what is the expectation mean squared. So it is same like what we did for your your ANOVA, except that you have a blocking factor or a nuisance factor which influences your output that you want to block. The reason behind blocking is your mean squared error gets reduced, because there are 3 factors now, which is treatment, blocks and errors, right. So your mean square error comes down. Obviously if your mean squared error comes down, your hypothesis, your power of the test will improve, because your F test is based on mean square treatment over mean squared error. If your mean squared error comes down, then your power of the test goes higher. So that is the reason why you want to do a blocking, but notice obviously there is a drawback, the degrees of freedom goes down, okay. So the degrees of freedom will be lesser here, okay. So we had this identity, that is sum square error plus sum square treatment plus sum square blocks, and exactly like your ANOVA you have mean square treatment, mean square blocks and mean square error that can be derived. So mean square treatment is a function of tau I square, mean square block should be a function of beta squared, and mean square error is just sigma squared. So you can take ratios, and like ANOVA we had the row mean, column mean, grand mean, okay. And I have derived this, I have shown this how we get the 3 terms, the cross terms goes to 0 and we have the 3 terms, and we had the last class regression equations also written up, that was towards the end of the class. So there are totally how many parameters? A treatment, so A parameters, plus B block, so here B parameters, so A plus B, and then there is a grand mean mu which is 1. So A plus B plus 1 equation should be there. So the total number of equations as per rule 1 is A plus B plus 1, and the right hand side is nothing but summation of the times, number of times the date that parameter is present. So if you want to write mu, equation for mu, the right hand side will be y dot dot, because mu is contained in all data. So the grand sum of all the data is nothing but mu dot dot y dot dot. And if you want to talk about tau 1 is present in first row, so the sum of the first row is y1 dot, tau 2 is y2 dot, and similarly b1 if you want to write about beta 1, that will be tau column wise, that will be y dot 1, y dot 2, right, up to y dot b. So that is the right hand side, okay, that is straightforward, rule number 2. Rule number 3, the left hand side of the normal equation is nothing but summation of all the parameters. So you write down all the A plus B plus 1 parameters, multiplied with what? Pre-multiplied with the coefficient that is equivalent to number of times the data that parameters appear in the right hand side. So if you look at mu hat, if you are writing equation for mu is how many times mu is present in the right hand side? Total number, which is nothing but A times B or capital N if you want to call it, that is why AB. And tau 1 dot is tau 1 hat, how many times it is present in y dot dot? A times. Tau 2 dot is also, tau 2 hat also will be present A times, the number of rows, and betas will be present B times, that is what the tau will be present B times and beta will be present, the rows and columns mismatch, tau will be present B times and beta will be present A times, that is what we have, okay. Then the second equation, mu will be present how many times? For tau 1 it will be B times, and the betas will be present only once. So this is the left hand side of the equation, okay. Once you understand, then you have all the normal equations ready. Of course all these normal equations are not independent, you have 2 dependencies. If you sum the beta block you will get the first equation, if you sum the tau block you will get the first equation. So it is not totally independent, so there are 2 dependencies, and therefore you add 2 more equations, which is summation tau equal to 0 and summation beta j equals to 0, and therefore there are A plus B plus 1 independent equations. You can solve it and get the solutions, okay. You can solve all this A plus B plus 1 solution equations to get the solution. So this is what you will be obtaining. Mu hat solution is nothing but y bar dot dot estimate, tau I hat the estimate is y dot minus y bar dot dot, and beta j hat should be equals to y bar dot j minus y bar dot dot. These are your estimates of blocks, treatments and mu. So now what is pending? We need to derive the equations for sum squared error, sum square mean squared error, mean square treatment and mean square blocks. So exactly like your last time we can do all of this. So your prediction, your model is yi hat, yij hat is mu hat plus tau I hat plus beta j hat. You can replace the estimates. So this is what you have as your next predicted data point, because you are fitting a model, right. Once you fit a model, you should be able to predict the next data point. The next data point, if you substitute for your estimates, is this one. Okay. So now the model is mu hat plus tau I hat plus beta j hat. You can substitute your estimates from your least squares and use it for prediction. Remember, least squares we use it for prediction, we can do the same here. Now coming to the R statistics, the variability explained by fitting the model. The overall variability explained by fitting the model is what? Is nothing but mu hat times y dot dot. Remember, y dot dot is the total summation of the grand data, mu hat times y dot dot plus tau I hat into yi dot plus beta j hat into y dot j. This is exactly like your R mu comma tau in your ANOVA. Now we have added up for blocks as well. This is the overall variability explained by the model. Mu hat, tau I hat, beta j hat are the estimates, and tau mu hat is present in y dot dot. The right hand side of the equation is for mu hat is y dot dot, the right hand side of equation tau I hat is yi dot, and the right hand side of beta blocks is y dot j. That is what I am multiplying. So this gives the overall variability in the data explained by fitting the model, the overall variability obtained by fitting the model. Okay. You can substitute your estimates and get the overall variability. The R value of this model is here, the overall variability in the data explained. From that you can calculate the sum squared error also, right. Sum squared error is nothing but the overall variability in the data minus the variability explained by the model. The variability explained by the model is nothing but R mu comma tau comma beta, tau hat comma beta hat, that is here, and the overall variability in the data is yij the square of the data itself, yij squared. So if you subtract both, you will get the sum squared error. Okay. So that is how you derive the equation for sum square, the overall variability minus the variability explained by the model by fitting the parameters. Clear? So far so good? Okay. Now we need to know individually what is the, whether treatment is significant or not. That is our hypothesis, whether our treatment is significant or not. How do I reduce, how do I get it? I need to know the effect variability explained just due to the treatment alone. How do I get it? I can call it as R mu comma tau comma beta minus R mu comma beta. That will give me the effect of what? Treatment alone. The overall, the R due to the entire model minus the R due to the blocks, the remaining is what? Tau. So R full model minus R reduced model. R reduced model, how do I get? R mu comma beta, how can I get this? You can do a single ANOVA with what? With tau I equal to 0. So what will happen? This is your single ANOVA model, right. This is your ANOVA model, where I have did what? I have removed the treatment itself and I am writing out the model as yij equals to mu plus beta j plus epsilon ij. This is ANOVA model with blocks, treatment is 0. So now for this model I can use the ANOVA logic ANOVA approach and get the R mu comma beta. You remember R mu comma tau in your ANOVA, now I get R mu comma beta. Now the overall model minus R mu comma beta should give me the effect of tau. Okay. Remember I cannot use ANOVA model for treatment, then I have not considered blocks at all. Okay. My null hypothesis is what? Tau equals to 0. If null hypothesis is true, this is the model and this is the variability explained by the model. Okay. My alternate hypothesis is true, what is the model? R mu comma beta, tau comma beta is the model. Okay. If my alternate hypothesis is true, R mu comma tau comma beta is the model. If my null hypothesis is true, R mu comma beta is the model. Now if I subtract both, then I can know the variability explained by treatment alone. That is what it is. And then I want to see whether it is significant against sum squared error or not. That is the idea. Okay. So you understand why I do not fit R mu comma tau. If my null hypothesis is true, it should be R mu comma beta. If my alternate hypothesis is true, it should be R mu tau beta. Now if I subtract these both, then I get the difference between the null hypothesis and alternate hypothesis and see whether that is significant or not significant. That is what I am trying to do here. Okay. So that is why I am subtracting R mu tau beta comma minus R mu beta. Okay. So this gives me the variability due to treatment, variability due to treatment alone. Degrees of freedom are known to us, a minus 1 degrees of freedom. Okay. So you can, yes. So the R variance, it is always in relation to the overall variability. So if your sum square error is low, then it is good. Okay. It cannot be, or if you take some mean square error, sum square error divided by the the degrees of freedom, that should be lower. Okay. Variability explained by the model may be very high, but your variability in the data truly may also be very high. So it is always seen in relationship. That is why you take a ratio, F test. You do not just conclude based on sum square or mean square, because it all should be seen in relation to one another. That is why you take a ratio. Only by doing a ratio you can interpret, because depending upon the data itself things will vary. Your treatment may have explained large portion of the data, but the unexplained variability may be even larger, then it is not significant. Okay. So that is why always a ratio makes the sense, that becomes dimensionless. So if you talk about biomedical data, the units may be different. If you talk about, let us say, industrial data, the units are different, the variability is different, right. Our variability, heart rate variability, it does not go what 100, no normal person at a steady state. What is the variability you guess? You will have 40 to 100, 40 for sports, 100 for slightly abnormal, 40 to 100, 60 units. Your industry, many processes may not have 60 units of variation. Okay. Some process may have thousands of units of variation. So you cannot just rely on just that number, you have to take a ratio. Only when you standardize, normalize it, you will have something to say. That is why it is always explained versus unexplained. That ratio is what? Sum square error is nothing but unexplained variance. If you are doing another different hypothesis, whether blocks are important or not, that is if your null hypothesis is not on treatments, usually we do on treatments, but if you do hypothesis on blocks, then you can do the same analogy. I do a fit a model for treatment, but remember now my hypothesis is on what? Blocks, not on the treatments. Then I can do what? fit a treatment model tau I and then R mu tau comma beta minus R mu comma tau, that will give the effect of blocks alone, okay, that will give the effect of blocks, understood. So that way you have the effect of treatment separately, you have the effect of block separately, and you have the overall equations, all three can be are derived here, and these are the equations I have given it as something to remember, but you do not need to remember. Look at this, sum square treatment, sum square block, sum square error. Now I have given how to even calculate that one. This is sum square treatment, sum square blocks and sum square this thing. How do I get this? Have derived, we have derived everything here. So nothing untouched. So this is RCBD, okay. Clear? Any questions? We have started with the model, we have went through the importance of blocks, okay, drawbacks of blocks, advantages, your degrees of freedom goes lower, but your power of the test goes higher, okay. So you can do better if you have blocks, okay. So I have given an example problem. So the blocking has a cost which is nothing but you lose b minus 1 degrees of freedom, because when you do not do blocking your degrees of freedom is what, a into b minus 1 for sum squared error, okay. Treatment degrees of freedom is same, a minus 1, your sum square error degrees of freedom is a into b minus 1 if you are doing without blocking. If you do with blocking, this is a minus 1 into b minus 1. So what are you losing? You are actually losing b minus 1 degrees of freedom when you do blocking. That is, if you close your eyes and always do blocking, that is also a problem, because you are going to lose degrees of freedom. That degrees of freedom is essentially what? You have to repeat the number of times the experiment, okay. What is b? B minus 1 is, each one is a experiment outcome. So you are simply sacrificing b minus 1 experiments if you are doing blocking. Remember that if you are doing blocking, you are simply sacrificing b minus 1 experiments. If you are doing blocking at 10 levels, you are giving up 9 experiments, okay, that is what it is. So the moment you start blocking, that comes up with a cost, that comes up with a cost on the experiment, okay. So if you want to design an ANOVA versus RCBD, the problem with RCBD is most often it will demand an RCBD or even better than that, but the moment you start blocking, remember you have to increase the number of experiments, okay, it has a direct influence, and how many times? That is equal to the number of blocks times minus 1, which makes sense, right, nothing comes at a free. So this the reason why we learn is we systematically know what are we going to do if you increase the number of, if you change the blocks or if you increase the treatment numbers, what is going to happen, how many experiments you have to do if you have to do something statistically show some results, clear. So this is what blocking cost is, and the advantage of blocking, as I said, is mean squared error goes down. So what is the advantage benefit of blocking? Quantitatively mean squared error, SSE for ANOVA minus SSE for RCBD, that difference is what you are getting as an advantage, you understand, technically that is what you get. Your SSE is for ANOVA is the overall, and for RCBD it is different. That difference in SS, that difference is what you get as advantage, or in other words, if you want to take a look at it even, so this is what you have, a into y dot j bar is y bar dot dot the whole square, that is the variance you are benefit you are getting, actually that is the quantitatively the benefit you are getting due to blocking, because that much variance you are pulling out of noise from the sum squared error term, you are pulling out this much variance outside and treating it as separately. Now if the moment by looking at your data set itself, you should be, if you watch your data set carefully, that should itself tell you whether it is worth going for blocking or not blocking, because if this y dot j bar minus y bar dot dot the whole squared is significant, or is there a significant variation along columns of the data, then you should know that you have to go for, it is worth to go for blocking. If there is no significant variation along columns of the data, then stay put, ANOVA should be good enough. Okay. So, just by looking at conducting experiments, a few experiments, you should know whether you should do a blocking or not blocking. Okay. That is why a few initial trial runs are done before doing any kinds of experiments. The usual model adequacy checking is all usually probability plots. Do not even try this chi-square, fit, etc. It is as complicated, that one problem will take you forever. A simple probability plot, normal probability plot should tell you whether it is decent, normally distributed or not distributed. Okay. So, I will do you one question. Suppose you have missing data, how do you handle? Suppose you have missing data, you have experiments, some values did not come out, you observe, you are not able to observe. Should you discard the complete experiment? I mean, I did not get the result for one experiment or one block. Should I throw it? What should I do? Let us say you all know about power meters, collecting power data, everybody knows that. I will take a simple example, right. So, I collect data from some, let us say some 100, or in IIT Madras there are about 5,000, 10,000 people are there, okay. So, some let us say 100 plus houses I am collecting data, power data. You all know about today meters can measure every second data, right. Do you think their data will be completely present? Will there not be any missing? There will be quite a bit of missing data, agreed, because you are collecting every second, quite a bit of missing data will be there, right. Now, there are two ways to look at it, okay. One, this data can be looked at as a vector from a house, or this data could be looked at as a matrix. Why is it a matrix? Remember, power consumption between me and my neighbor, will it vary drastically? Is he going to have a electrical hybrid, a crore car compared to me? No. More or less our utilization will be same. If it is two income group, two people working, you know the usage pattern, morning and night, daytime near 0 except for fridge, right. And if you talk about single income, that is a very different. So, there are patterns. So, I collect them and then put it as in a matrix, very simple, you have a matrix data. Now, there are missing data, how do you fill it? The simplest way is to look for mean, right, history based on, but remember mean is also sensitive to outliers, right. What are we trying to, when you are trying to fill the data, what do you mean by filling the data? What do you want to achieve? What do you want to achieve when you want to fill the missing data? This missing data is very, very important, and I can give you a same example in your brain waves. Do not think I am picking up electrical this thing, it is same across. Your EEG data, will it not have missing data? You have sensors placed, some 12 electrodes, 14 electrodes or 36 electrodes or 64 electrodes, 128 electrodes, data will be missing. How do I complete it? How do I handle this missing data? If you throw the missing data, which is easier, you have an abrupt change in the data pattern, right. You have a change in the pattern because there is something, suddenly something changed and you have a different. So, to ensure smoothness of the data and for all other practical purposes, you want to fill the data. How do you fill it? Is mean the only way mean is subjected to outliers. How do you do this? But what is the overall point? When you fill in this data, you do not know that missing data, you are filling in. Now, should it play a major role in the outcome? If my missing data is determining your result, is it good or bad? Bad. So, how do I make sure that? But the overall idea in a matrix, so what I said, this particular missing data point should not influence your output. So now I have a matrix, okay, I have a matrix. So in the matrix, do you all know about norm of a matrix? You have heard of norm of a vector? What is norm of a vector? Second norm, what is second norm of a vector? Square root of, it is nothing but Euclidean distance kind of square root of x1 square plus x2 square, x2 3 square, etc. right. That is, if you take between two data points, it is nothing but the distance between 2 points. Now one of the ways in which people fill missing data in a matrix in this kind of situation is that data point should have minimal effect on the norm of the matrix, like a norm of a vector. So you can same thing, you can use it for filling the data point vector also. Your norm should not change much because of filling the data. Of course you can use other relationship like correlation relationship in the columns, relationship in the rows, all of them should not change because of the missing data. You want to fill the data, but this data point should not influence your result. You should fill in such a way that the data point should not influence your result significantly, and that is where we want to say correlations, relationship should be preserved. Just do not look at the mean, mean is one dimensional, you are talking about multi-dimensional. So relationship should be preserved, the norm of the matrix should be preserved. Those are conditions which are typically used to handle missing data. In experiments we will definitely have missing data problem, okay. It could be a vector. Now today experiments you typically get matrix of data which is a matrix, not just a vector. So when you talk about a matrix, you should be very clear that when you fill the data it should not influence your result. So one of the ways in which people fill is using minimizing the norm of the matrix. You fill the data such that you do not change the norm of the matrix or the norm of the matrix is minimal. That is one of the conditions based on which today people handle missing data. It is a very practical problem, every experimentalist will face it, missing data, and there are several ways to fill it, the missing data, and today the state of the art uses matrix norm minimizations to fill the missing data. I just had a slide so that you understand that missing data is also something very important.